So last week in Tuesday's class, we started discussion about dimensionality reduction. So just as the rehearsal, that why do we use dimensionality reduction? Is because sometimes we have like very large number of features or parameters in a data set. Like in the Bayesian networks, we have seen that we need to do this n square number of computations if we want to go for a fully connected network, all the joint probability distribution, or in the say something like a maximum margin classifier, you need to the computation typically is in the order of the data set. So, typically is in order of the number of the features, and the number of the features or the parameter, it can be order of 100, like 100, 300 dimensional vectors or more. So what happens, and typically like we iterate them over say like 1,000, 5,000 number of data instances, if not more. Particularly in deep neural network, we iterate over a very large data set. So that increases the computation overhead and also the space complexity, because at each step it is matrix multiplication, right? So however sparse the matrix is, still you need to store some of the parameters, some of the in-between computations. So this also consumes a lot of space, and space not only in terms of the hard disk space, but actually the running memory. Okay, that's why we have the CPU, GPU, and now TPU. So, and there is another reason, that's why we do dimensionality reduction, is that to visualize the data. See, as a human being, we can only think in terms of like 2D or 3D, right? Whereas my data set can have 100 features, or each data instance can be represented in a by an 100 dimensional vector. So that means that data instance is a point in a 100 dimensional space. But we cannot visualize that. All the examples that we have seen in the K-mean clustering, if you recall, we have seen it in the 2D. And that actually helped us to understand the intuitive logic behind clustering. But if I am having a real data set and say I have ran a loop of clustering, and I want to see how good the data set is separated, or sometimes I want to see that if I like how exactly my data looks like. Sometimes even before running anything, I can try to run a loop in the pattern of the data set. So then how do I do that? So for that I need to somehow reduce the plot from a 300 dimension to a 3 dimension. Now I cannot do it randomly. If I do it randomly, then actually what I am seeing and what actually the data is will have no correspondence, and all my calculations and understanding will be wrong. So, and also it not only enables us in data visualization, but it also saves my cost of observing each feature, going through the feature specificities, and it is more the interpretable also. Say the if you have many features, like many dimensions to represent a data point, that means those many variations can be there in a data point. So each time you need to account for like all the variations across all the different feature dimensions. But if you can reduce the dimensions itself, that means it becomes more interpretable, and there is also like we can come up with simpler explanation for our understanding and for also the model performances. And many a times what happened, why we say is that for deep neural network we need order of thousands of data points, because we have so many parameters to train based on the neural network layers, based on these the input dimensions, based on the embedding dimensions that we choose. So if my data set is smaller, and on a small data set, if I want to train that many number of parameters, it may overfit or it may not be stabilized at all. So that's why sometimes simpler models are used. Now, how do we use simpler models? How can I come up? Like, how can I say, okay, these two features are more important from the all the others. Now, all these two uh, in all these situations, the method of dimensionality reductions are very useful from a machine learning perspective. Now, uh, there I believe in the earlier classes you have learned about the feature selection, particularly before the decision tree and the ensemble classification, that how based on the gain of each feature like this chi-square values, how can we choose from a set of features a subset of important features. So one such algorithm is subset selection. So in feature selection, what do we try to do? We want to choose, k important features where k is significantly lesser than d from a set of d features, and we ignore the remaining d minus k ones. So basically, I am coming up with a smaller feature set, but in the same plane with the other features. But whereas in the feature extraction, what do I do? Instead of choosing a subset of the feature, I project the original features from a d-dimensional space to a k-dimensional space, where k is significantly lesser than d. So basically now if my original features look like the x1, x2, x3 dot xg, so now my transformed features are z1 to zk, whereas this number k is very less than number d. Now what I am doing in this way, I am not ignoring any features, but rather I am taking all the features and I am projecting from d dimension to k dimension. Now how can I do that? So before that, let us see what are the some difficulty in this subset selection algorithm. So as we have discussed last week, so for d features, there can be 2 to the power d possible subset. So we can either do the forward search or the backward search. So what we do in the forward search, we start with a null set, and as step we incrementally add one feature so that my the error function is minimized. And in the backward search, I do the opposite. I start with all the features and remove one feature at each step, so that in such a way my the error function does not increase beyond an arbitrarily chosen small value. Okay. Now these has the complexity is d square, which is like if you see it's like for say like 300 dimension, 500 dimension, which is quite large. So, and there is another and in between the forward and the backward, there is something called a floating search, which at each step adds say like certain k number of features and to remove certain L number of features. So, but all these have a large time and space complexity, and also it may not be possible that if I have some specific k set beforehand, all the features variations are captured. So uh, this, this. In okay, so this is an example on the forward search of the forward search algorithm on the Irish dataset. So Just a moment. The Irish dataset is a very well-known dataset on pattern recognition, and it is being used for a long time. Sorry, today. Okay, so I have also the Irish dataset open. So you can download the Irish dataset from the UCI machine learning repository, and you will see, or if you look into different machine learning papers, you must have come across that Irish dataset is one of the most frequently mentioned. Okay, so it is used heavily for pattern recognition, and it is basically a planned classification dataset. Okay, so that's why this dataset has been used for the example. So, but it's shown here that if we start incrementally from say like F1, F2, like say one feature, and then we start with two features, then we start with three features, and we see that how good the feature selection, uh, segregate my different data instances, and based on like where we have a satisfactory segregation, we choose the feature. I think the other details are in the book chapter, so you can go through that. So, and it shows that after F3, like at each step, if we add, say, if we only have F1 and F4, F2 and F4, and F3 and F4, then how the data plot it looks like. So, we see that with F3 and F4, the data are segregated well. So, that why this F4 is chosen uh, as the subset of features. Okay. So now from the subset selection, we move on to actually the dimensionality reduction or the feature extraction. So one of the most well-known form of feature extraction is or dimensionality reduction is principal component analysis. I believe you have plotted data with PCA transformation in your lab classes. Yes? Anyone? Yes, no? Okay, so if everyone is silent, that means either nobody is listening or it is yes,
No, ma'am, we have not done.
yes.
No, we have not done that in the lab.
No, have you? So I think that you have plotted the data, right? Like using Matplotlib or something.
Yes.
Yeah. Yes. So there, how did you plot the data in 2 dimension? Just using Matplotlib. There was no need to call the PCA explicitly. Like, was there something, some function like PCA, like the function call, things like that?
Yes, we did that in one of the assignments.
Yes. So basically, so see, even for your like basic classification, you have to plot the data from a higher dimension to a low two-dimensional space, right? For your understanding, and you have realized how much that helps. So typically, it is done using the principal component analysis method or PCA method. So how do we do PCA on a data set? And here once again, I request everyone that please write down the steps in pen and paper with me. Okay, just so that you can understand and you like your muscles also learns like how did we derive PCA. Okay, so the objective in PCA is find a low dimensional space such that when X is projected there, information loss is minimized. So as we have discussed, say my X is with 300 dimension features, which is very common if we use some embeddings like what2vec, or even if you have represented data in TF-IDF or any other numerical vector form. So you know it is quite high dimension, like order of 100 or so. Yeah. Okay, so but the thing is that if I want to project the data, say on the two-dimensional space, so what is happening now? My data point is a point in a 100-dimensional space. So you can intuitively think, so 100 feature means, so how did we say that it is a feature? Based on that, if there is a variation across that feature, then two data instances having different values for the same feature will be significantly different data instances, so that the feature can separate data in a good way, so that we can, when we feed that particular feature to my classifier, so my classifier will be a better classifier. It will learn to segregate two distinct data points based on that variations across that feature dimension. So now if I have 100 dimensional features, that means there is some variations across each of these 100 dimensions. So the degree of freedom is very high. Now you are compacting all these things and putting it in a two-dimensional space. That means from these variations across each of the 100 dimensions, you are now coming down to the variations only can happen along two dimensions. So basically what is happening, that there is the scope of the information loss. So we lose some of the feature specific the information as a cost benefit trade-off of dimensionality reduction. Now what PCA tries to ensure is that these information loss, that when I am compacting from 100 to 2, this information loss is minimized. And how do we ensure that, or how does PCA ensure that, is in the derivation. So say for example my X is the, the original d-dimensional features, and I will project X on the direction of W, which has say like k dimensions, very less than d. So from basic coordinate geometry, the projection of one vector, so X is a d-dimensional vector and W is a k-dimensional vector. So the projection of one vector onto upon is their multiplication, right? So then the projection of X on the direction of W is Z, and Z will be equals to W transform X for the matrix multiplication. Now what my objective is that these,
You mean the other components of W will be zero.
sorry,
I mean, if there are n components in X and there are only k components in W, then n minus k components of W will be zero, right?
yes, so W does not have n minus k components.
But like if we are multiplying them, then their dimensions should be equal, right?
Yes, yeah. Okay, just let me calculate the dimensions. So, okay, okay. So basically, see, the thing is that these are the whole matrices. That the okay. So X is like this. Say I have n data instances, and my the X is D. So this is the n cross D, and W is the n cross K. So W transformation is K cross N, right? So K cross N into the n cross D.
Okay.
Okay, yes. So basically my objective is that this Z, I need to maximize the variation of Z. So let me see that if there is an A. So basically what I am trying to do is that, please pardon this bad drawing. So say the X was a, say, like, 5-dimensional feature. So as I cannot draw 5 dimensions in a 2D plate, so please assume that all the 5 dimensions are orthogonal to each other by definition. And here at this point somewhere was my X. Uh, say this was my the original, like the one of the rows from X, a 5-dimensional data point. So now what I am trying to do is that from 5 dimension I am trying to project the data point in the 2 dimension, which is my W. Okay. So now in this 5 dimension means there are some variations across all these dimensions. Say a feature can vary along like, this much variation. This may have a very high variation. This feature is having some low variations. This is having super high. This is having, medium. Okay. So now all these variations, like all these are the information in the 5-dimensional space. So when I am compacting it to a 2-dimensional space, and my objective is that my information loss needs to be minimized. That means what is my information? These variances within the features are my information. That means how with different values of the same features, how distinct my different data point is, how far or similar they are, correct. So that means when I am projecting it into 2 dimension, I need to ensure that I choose the 2 dimension such that the variance of my feature set along this 2 dimension is the highest. So this is not equivalent to taking the 2 highest from this 5 and plot it in 2. So I come up with this such that along these 2 dimensions, I will have highest variations in my feature set or for my data, right? So that's why to minimize this, my objective, this function is that that variable of Z should be maximized. Okay, because there can be a confusion that once we are saying minimize and then they maximize, so that is the reason this variable of this variance of Z is maximized. Now, what is variance of Z? Variance of Z is variance of WTX. So from the probability that we know that this is the expectation of WTX minus WT mu square, whereas mu is the mean of X, right? So that means, and this is whole square, so we can break it into 2 components. Okay. So now we can take this WT like WT into X minus mu and X minus mu transform W. Sorry, transpose W, right? So that means if I take this WT out, this will be expectation of X minus mu into X minus mu transposition into W. That means WT sigma W, whereas this sigma is equals to the variance of X. So basically based on the variance of X and based on our target dimension, we are coming up with the projection. Okay. So clear till this point? Yes.
Now, what are the dimensions of X? Can you repeat again?
So dimensions of X is the dimension of the original feature vector, and
No,
dimension
like
of W
you
will,
said, it is something n cross. Can you repeat that part?
sorry. So the n I said is the number of instances.
So X is a matrix, right?
Yes, X is a matrix.
Uh,
Matrix or vector, like anyway this calculation holds.
Like if X is a matrix, then the number of rows would be the number of data points in the
Data point.
data set,
Yes.
and the number of columns would be the number of features, right?
Yes. Yes. Number of features. Yes.
And similarly, what would be the dimensions of W?
Yeah. For W also, see, if just give me a moment. If if X is, say for example, if X is a matrix, then X is the n cross D. Okay, and W is the n cross K, whereas K is less than D. So each vector, if I say like X is a vector, so it will just be 1 cross G. So this is same thing. And this will also be 1 cross K. So in either way, like this W transposition, it will be either K cross N or K cross 1.
So Z will be the new data set with less information.
Is Z is the projection, like Z is the how can I say that? Basically, Z is not the new data set. We are not changing the data set. We are plotting the same data set from say from this 5 dimension. Now I will plot the same number of data in this 2 dimension. And how do I come up with this 2 dimension is based on the maximization of the variance of Z. So Z is a variable here. Z, like this.
So can we say that like we have only chosen K out of the D features, so like we are selecting the K most important features and defining new data set Z?
No. That is the difference between PCA and the subset selection. When you are selecting the subset, so basically what is happening, the original features are kept intact. Say for example, I represent, say I have a data which is housing price. Okay. So now my housing price is basically say for example you dependent on say the location, say closeness to metro station, closeness to rail station, the weather, the housing has a community room, on which floor is that, based on the square meter floor area, whether there is lift, or whether there is 24 hours electricity, whether there is some generator backup, say like 10 things like this. And that is my indicator of housing price. Okay. Now, in subset selection, where as you said, like we can choose 2 most important features, what would I do? I would have seen that, okay, not 2, let us come to an agreement of 3. So I see from this all these 10 different things, most important 3 features are: first, if there is a generator backup for electricity runout, if there is a lift, and what is the closeness to the nearest rail station. Okay. So now I am choosing a subset from the original feature set only, based on some mathematical model or based on some survey based observations, that this is how most house buyer decide on how to buy a house anyway. And we do the modeling on these only 3 features. So that is my subset selection. When I am coming to principal component analysis, say I want to choose, like I want to now represent these 10 dimensional features. I want to do a plotting in a 3 dimensional space and see that how, depending on each feature, how the different housing price clusters look like. So in that case, I will not choose 3 out of 10. I will project from 3-dimensional space, from 10-dimensional space to 3-dimensional space. Now these 3 dimension, these 3 features are my derived features. They are not any particular generator backup or any particular proximity to rail station. All these 3 features are actually projection of all the 10 combined. Okay, so that is the difference. And we have chosen these 3 dimensions such that my variations along these variants along these 3 dimensions are the greatest for this particular data set. Was I clear?
Yes, ma'am. But like I have one more doubt that
Yes.
like what would be the dimensions of Z? Like if there are n data points in the X, then there should be n data points in Z as well, right?
So no, so yeah, so Z is the anyway K cross G. So we are choosing Z so that if I project from D dimension to K dimension, or the variance between K dimension and D dimension, this variance of Z is highest. Basically, I am choosing K dimension such that if I project from my particular D dimension, this K dimension will correspond to the highest variations. So Z, if you see in the expression of Z, there is the n or 1 is not featuring. I am not changing my original number of data. My number of data is
But there is no n in the dimensions of W.
yes,
So
yes, yes. So because I am not optimizing on n, I am not touching my number of data points. I am just doing the calculations on the dimensions. You don't need n because see, this is not your model. This is not my mathematical model. This is just my feature extraction. Okay. So even after doing PCA, you need to run the support vector machine or logistic regression or ensemble classification. This is just my feature extraction. It is just another way. Say for example, how in a feature or how in a particular data set, how do you choose 10 features? By some feature importance, or by that there are 10 feature dimensions which have particular values. So this is just another method of say like choosing or extracting 3 important feature directions from my 10 features. Okay. This is not my classification. Understood? This is just my feature extraction. I am just extracting feature to represent each data point. I am not doing any training on the data point. Was I
okay,
clear?
okay, ma'am.
Okay. Okay. So as we see that the variance of Z can be expressed in terms of my feature like the number of target dimensions and the variance of the original feature set X. So basically if I transform this, so what happens is like this equation can be expressed like to maximize variance of Z. So it is also I put a constraint that my value of W will be 1. So why do we do this? So in a very simple thing. So basically we will see very similar to that. What did I teach you before this? This spectral clustering. These W's are the eigenvectors actually for the uh, variance matrix subset. So the thing is that actually this W1, W2, what all we are saying, this is these are nothing but the first eigenvector and second eigenvector of my variance X matrix. Okay. So basically, we for principal component analysis, what we are trying to do is to find the first largest the first eigenvector corresponding to the largest eigenvalue, second eigenvector corresponding to the second eigenvalue, because the beauty of the eigenvectors are that they are orthogonal to each other. That means at 90 degree, that means they are, their dot product is 0. So they are independent of each other. So we choose the eigenvectors in the order of their like magnitude. Okay, like in a descending manner. So basically now if I want to, I have used too many basically. So now actually if I want to use, or if I want to project A in a two-dimensional space, what do we really do is that we find the eigenvectors in descending manners of in descending the order of the corresponding the eigenvalues, and we choose the first two the eigenvectors. If I want to from x, if I want to plot x in a three-dimensional space, I choose the first three eigenvectors corresponding to this variance matrix of x, and that is what you exactly do when you plot your data set in a two-dimensional space. Okay.
Ma'am, so W is like just a mapping relation.
W, yes, W is not the relation. W is the mapping target, target mapping space. Okay.
And what do you mean by a mapping space?
So my W is, say for example, if I want to project from 10 dimension to 2 dimension, my W is the W1 and W2, these two dimensions. Okay. And how do I choose W1 and W2? W1 and W2 are the eigenvectors of the variance of X matrix. Okay. So so each vector is in a dimension, right? So this is how we choose
So can
W1.
we call that as just a transformation relationship matrix?
Yes, so it is a feature transformation. We are transforming a d-dimensional feature to a like a d-dimensional data instances or a d-dimensional feature vector to a k-dimensional feature vector. Okay.
Okay, ma'am.
Okay, so basically this is a graphical description. Actually, the problem is that it should be accompanied by the book. Now the book does not have an online version, so it shows intuitively what the PCA does. Say I only have a two-dimensional data point, and from two-dimensional I am projecting onto the another two data dimensions. So these are the Z1 and Z2 are the two directions of my two. The first eigenvector and the second eigenvector of the variance of X matrix, and it basically, what PCA does is that it basically rotates these Z1 and Z2 to be the 90 degree, like to be the main axis, and it plots the data at the origin.
Ma'am, can you go to the previous slide?
Yes. Yes.
Ma'am, in this on the right side of beta, is it W2 transpose W2 or W2 transpose W1?
No, this is W2 transpose W1 to ensure this property. This orthogonality with W.
Okay. And the first condition is for what? So that the norm of this is
The
1.
norm of W is 1. So So if we implement this condition, then only these W1s will going to be the eigenvectors. If you recall spectral clustering, there also we had imposed the same condition, so that at the end the result are the eigenvectors. Okay.
And these alpha beta values can be anything.
These alpha beta values are just the coefficients for the optimization function.
Okay, okay.
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 So this alpha, it is coming from, it is the same equation till this part to find W2, and this part is to ensure that W2 is indeed orthogonal to W1 because of the two things, because the eigenvectors are orthogonal to each other, and also because of the things that only along two orthogonal dimension. Why do we always plot like features? Why do we always say they are at 90 degrees with each other? Because only along two orthogonal directions the variations will be highest, and the direction of the one feature will be independent of the other. Sorry, not direction. The variance in one feature will be independent of the other. So in that way, we will ensure the maximum separability we have the good features to separate the data instances of the class. So till this point, is everything clear? Okay, so now just a small trivia that most of the times we have the K predetermined. Like, I want to plot in a two-dimensional space, or I want to plot in a three-dimensional space. But if I need to choose K, how do I choose K? So K is there is something called a proportion of variance. It is the variance like the along the d dimension. I think these lambdas are the eigenvalues. Just a second. Okay, so this proportion is of variance in the is the ratio of the sum of the k eigenvalues of the k dimensional target feature space, and the sum of d eigenvalues of the d dimensional the original feature space. So don't get overwhelmed by like all these eigenvalues and the different dimensions. So basically this is a ratio to derive the value of k, and this k is and we stop at where the proportion of variance is 0.9, and basically as you have also seen in the different clustering, the same the elbow method, we cut at the elbow point, that where we reach the elbow of the like the graph of eigenvectors and the eigenvalues, we cut at this point. If you see this graph, eigenvalues and eigenvector, and this graph, proportion of variance and eigenvectors, has the elbows at a very similar point. So we cut at there and say, like we say, we will have this 10 dimensions or the 20 dimensions for the resultant K. So this is how. So when you plot actually with PCA, so don't go into this opt digit and all. This is a data set for digit identification, optical recognition of handwritten digit identifications. Okay, so when you plot with PCA in the 2 dimensions, so the 2 dimensions are actually the first eigenvector and the second eigenvector. So now you see the difference, that if you have chosen say 2 features from the original 10 feature set, these 2 dimensions will be something like the house location and the generator backup. But now these 2 dimensions after PCA is first eigenvector and the second eigenvector, and the data is represented in terms of its position in this 2 vector dimension. Okay. So am I clear till this point? I know it is not very clear. Lots of questions and confusions can be there. I will also try to find that if I can have the PDF chapter of the book or some other reading materials on the book, I will surely forward it to you. But more or less, why are we doing PCA? And the PCAs are nothing but the first and second eigenvector of the variance of the original feature space matrix. I think this much is clear by this time.
Yes, ma'am.
Yes. Okay. Okay. So I will stop today's class here.